good, thank you for asking. How are you? Happy to be in school?
Yeah, I love this class.
I know. And you know, when we learn about characters like Erwin,
It's so fun.
it doesn't get better than that. Yeah, I'm gonna get my mouse. I almost need 2 mice.
Where do you want us to turn our laptop?
What?
Where do you want us to turn our laptop?
Up here at my desk. Unless you typed it, and then you can put it in classroom. All right, are we ready? Need another minute?
Can I just like turn my notebook and leave it at the end of the
Mhm. And I'll give you a sticky note so you can tell me what page. Okay. So, let's start with the second bullet point up here. Derived an equation that treated electrons as waves. Now, yesterday what we talked about is the Bohr model, although it's a great teaching tool for us, it can't be the model of the atom because Heisenberg's uncertainty principle tells us we can't know where the electron is and what it's doing at the same time with any kind of certainty. Remember I told you that means we're going to have to use probabilities to really have some good idea of where it might be, but we can't know with certainty. So Erwin's job was to determine the probabilities of where we could find these series of electrons. Makes it very complex because with hydrogen we only have 1 electron, but if we move to helium, now we have 2. And lithium has 3, and so on and so forth. Uranium has 92. So we've got a lot of electrons, and they can't all be in the same location. We know that's not possible. But his job was to determine where it is most probable that the electrons are going to exist. Okay? He did that mathematically, which is really good for us. Because the equations that he wrote are for 3-dimensional space. The equations that you guys write in Algebra 2, Algebra 1, geometry, whatever, those are for 2-dimensional space, right? An x and a y. But in 3-dimensional space, now you have an x and a y and a z. So you've got an axis that goes up and down, you've got an axis that goes side to side, and you've got an axis that goes in and out. Right? So we've got a 3-dimensional axis, and the wave equations that he wrote describe 3-dimensional space. These 3-dimensional regions that have the highest probability of locating electrons are called atomic orbitals. I'm going to show you a picture of them here in just a moment. I do not want you to panic until I tell you it's okay. It is not Tuesday, so no tears can be involved. But they look pretty funky. That region, that 3-dimensional volume of space is called an atomic orbital. We're going to talk about atomic orbitals a lot. But the most important piece of information up here is that his wave equations work for every element on the periodic table. They predict the atomic emission spectrum for every element accurately. So, let's look at the orbitals. In a moment. I'll show you a picture of them first. I think you have a picture of them in your resource packet. I think it is this picture. Have you looked through your resource packet and seen this? Nope. Well, maybe we should get those out and take a look. Go on the back of the third page. Up there at the top. See that picture? Okay. So I think it's important that maybe we have this out and looking at it as we discuss this. I gave you this picture so that you could always have it right there for you. But I want to point out, we'll go back to the words here in a minute, but I want to point something out here. Can you see the X, Y, and Z axis? We took the typical Cartesian coordinate system that you use in math class, and we laid it down this way. It looks like it's this way, but laid it down that way, and then the z-axis goes up and down through that. They all cross at the origin, 0, 0, 0, but the z-axis works just like the other two, up and down, positive and negative. And you can see that that's the same axis we use for all of these. So we'll come back to this picture and talk about it here in a moment, but let's go back to the words. So atomic orbitals are regions of space, three-dimensional regions of space. They're fuzzy, clouds. They don't have boundaries to them. It's not like, you know, those plastic Easter eggs that you can get, you open them up and you can put candy in them, and then you can pop them back together. Do you know what I'm talking about? So it's not like that. It's not like anything that is going to contain the space inside it. It's just a volume of space. And it is really where you have the highest probability of finding an electron. That's all it is. It's a region of space where the probability is high that an electron will exist in an atom. So then just a couple of other facts about atomic orbitals. One is that they can hold 2 electrons. That's it. Each atomic orbital can only hold 2 electrons, no more. And then the lower the energy, the higher probability that the electrons are closer to the nucleus, which is something that Bohr's model accommodated, right? The lower the energy of that energy level, the closer it was to the nucleus. The same thing is true here. The lower energy that the atomic orbital is, the closer to the nucleus it is. Can electrons exist in the nucleus? No. When an electron forms in the nucleus, in a situation where we have a nuclear decay, the electron is ejected. It is not allowed to be in the nucleus of the atom. So there will never be electrons in the nucleus. The probability of finding an electron in the nucleus of an atom is 0. Questions about that? Okay. I guess we have to talk about the orbitals. So let's just look at these for a moment, because it's not as straightforward as this. If each atomic orbital can hold 2 electrons, and that was the only set of orbitals that an atom had, what's the maximum number of electrons it could hold?
Well, wait, is that like one at the top, one?
Yes, the red one is 1 orbital.
So the yellow, are those all that like make up the ring?
Each coordinate system is 1 orbital. Okay? okay? So, let me restate that question. If this was the only set of atomic orbitals that every atom had, how many total electrons can it contain?
32.
Well, do we have atoms or elements that have more than 32 electrons? Yeah, uranium has 92. Lead has, excuse me, lead has 82. Zinc has 30. This isn't going to accommodate everything, so it's more complex than that. Of course it is, right? So we refer to these as our orbital sets, okay? Our orbital sets. Only some sets are available in certain energy levels. So Bohr's model was mostly wrong. But there are aspects of Bohr's model that are correct. One of them are the energy levels. The energy levels are correct. It's just not like Bohr depicted it. So we're going to combine the idea of having energy levels with this idea of having atomic orbitals, and some of these sets are going to be available with certain energy levels, and all of them are going to be available with other energy levels. So let's just talk about the shapes here, and then we're going to learn a little bit about another piece to the puzzle, and then we're going to come back to this, okay? And again, I'm just going to ask that you trust me, because this is going to be, we're learning a little bit about this, a little bit about this, a little bit about that, and then we're going to be able to put it all together. But we got to have a little bit of information to make us dangerous. So if you look at this orbital set here in red, this is the S orbital set. You can see the little S down there. This is the S orbital set. There's only one orbital in that set. It's spherical, and I mean, that's pretty much all it is. Like, that's the first orbital that's available in an atom. The next orbital set, and these increase in energy as we go down. So the next orbital set are the p orbitals. And you can see a little p here, and each one has a little number after it. That's a subscript, -1, 0, 1. We'll get to that later. But the shape of these, we refer to them as dumbbells, because it's got a lobe on one side and a lobe on the other, and in the middle is what we refer to as a node. It's a place where there's zero probability, okay? So these are actual three-dimensional regions of space where electrons can be located. They're incredibly tiny regions of space because electrons are really small, and these are all contained within atoms. But there are 3 p orbitals because you can orient this set of lobes in 3 different ways. This one's along the x-axis, this one's along the z-axis, and this one's along the y-axis. The shapes are identical. The only thing that's different is the orientation. Okay? The next highest energy is the d orbital set. And you can see there's a little d here by each of those, and they also have a subscript, -2, -1, 0, 1, and 2, and these ones are a little bit more complex. We refer to this set as double dumbbells, and then there's one oddball, it's in the middle. It's a dumbbell with a donut. I don't know, this is what Erwin Schrödinger calculated. Makes no sense, but okay. So we've got 2 of these dumbbells that are lined up. These are lined up on the x and y. These are lined up on the x and z. These ones are lined up on the y and z. And these ones are, they're like between the x and y.
What's the middle one thing?
This is a dumbbell with a donut around it. So you really have 2 spheres and then a region that looks like a donut in the center. And the subscripts, we've got -2, -1, 0, 1, and 2, and those numbers are important, but we'll get to that later. The last one is the f orbital set. These ones are the most complex. And you've got triple dumbbells, you've got donut, you've got 2 donuts and 2 spheres. These ones are really complex, all right? And they go from, the little f, it goes from -3, -2, -1, 0, 1, and 2, and 3, and that's gonna be important, but we'll worry about that later. But here's something I wanna point out to you. It's always a struggle for students to remember how many orbitals are within each set, right? We've got 4 orbital sets. There's 1 orbital in the S set, 3 orbitals in the P set, 5 orbitals in the D set, 7 orbitals in the F set. They're odd numbers, 1, 3, 5, 7. The orientations have an impact on how many there are. So in the S orbital set, how many ways can you uniquely orient a sphere in space? There's 1 orbital. Right. So you're going to become very familiar with these. So what I'm going to ask you to do, let's see, do I want to do this now? Yeah, let's do this now. No, we're going to wait. Okay. So I know this is not intuitive, but we're going to move on, all right? Because we use this information to help us identify the location of an electron, the likely location of an electron, right? This is probabilities. Nobody really understands probabilities except for Schrodinger, apparently, but this is what we have to work with. We're looking for the likelihood of locating a specific electron. So, you're going to need your periodic table out. Actually, you know what? Don't get it out. I'm going to give you a new one. I'm going to give you a clean blank one that you can write on, but you cannot use this for your test or quiz. This is really just for you to become familiar, okay? So, we're going to define 4 quantum numbers because we are, whether you like it or not, in quantum mechanics with this understanding of how the atom is structured, okay? So, I'm going to tell you right now what the 4 quantum numbers are. We're going to talk about them very specifically. We're going to label some information on our periodic tables, and this is going to eventually make sense. We're going to have to work with it a little bit before it does, but you got to trust me on this. It will make sense, okay? Oops, I'm sorry. So, for the 4 quantum numbers, the first one is the principal quantum number. We designate it with a lowercase n. The second quantum, and we do these in order. They're always in this order. N is first. The second quantum number is the angular momentum quantum number. The angular momentum quantum number. And it gets the designation that's a lowercase l. Okay? Second quantum number is a lowercase l. The third quantum number is the magnetic quantum number. And we designate that with a lowercase m and a subscript l. The fourth quantum number is the spin quantum number. The spin. And we designate that as a lowercase m with a subscript s. We identify these quantum numbers because it's like an address for the electron. If I looked up on Progress Book Chase's address, it would identify specifically where he lives. Start with the state. That narrows it down from all 50 states to 1. The city narrows it down from all the cities across the state to 1. The street narrows it down from all the streets in that city down to 1. And then the house number identifies specifically where on that street he lives. So each one narrows the possible electrons that we're trying to identify down to 1 electron. So when we write these quantum numbers, we're always going to write it for the last electron that's added to an atom. It's last electron. Okay? So let's go ahead. Let's just go for it. It's gonna be fun. Let me tell you a little bit about each quantum number. A lot of writing, I know. A lot of writing today. So, the principal quantum number, n, tells us the relative size and energy level of the orbital. This is the energy level. This is the energy level. As n increases, the atomic orbitals get larger. So if it has a higher energy, it's got a larger region of space. So major energy level values range from n equals 1 to n equals 7. We do not have any elements that have an n value higher than 7. So this is where you need the periodic table. Let me draw one over here in a color that you can see. If you do not get all the information that I present, you can always watch the video and get what you need after that. Okay, so here's my periodic table. The periodic table tells us the energy level. You ready? And the periodic table that I just gave you, I would put your name on it, and I would put at the top of it quantum numbers or something like that. And then I would take notes on that periodic table as well as notes in whatever notebook you might be using. All right, so I am going to identify the energy levels on my periodic table over here. And it gets a little funky. But up here, hydrogen and helium are in n equals 1. And the last electron that goes into hydrogen or helium will go into energy level 1 every single time in its ground state, because we're only doing this for ground state. If we tried to do this for excited state, your heads would float away. Lithium. And everything in that period is an energy level 2. Are we seeing a pattern? Sodium and everything that follows it is at n equals 3. Potassium, what do you think that one's in? N equals 4. So these correspond to the periods. Well, that makes life easier, right? Except there's a little catch in that. Okay. Nothing has there. Okay, let me say that so it makes sense. Everything has an exception in chemistry. So, if we're talking about the main group elements, we can use the periods to identify the energy level. If I want to talk about the transition metals, though, the energy levels are shifted 1. So, scandium, what is that, 22? 21. Scandium and everything in the transition metals in that row is n equals 3. But if you can remember that, that's good, because this is n equals 4, n equals 5, and n equals 6 that follow it. Everything's just shifted 1. Okay? Yes, Owen.
So scandium to zinc.
Scandium to zinc is n equals 3. Yep. and we've addressed everything except these two bottom rows down here. They're shifted 2. So this top row is n equals 4, and the bottom row is n equals 5. so if you can't see it, or you need to move closer, or you need to check it out later, I'll leave that up there. So that's the energy level. Principal quantum number, yes.
Why? That's different. I'm confused on why that's a foreign thought.
I didn't tell you why, I just told you they are.
Okay.
You gotta trust me. But you'll be able to explain why when this is all said and done. Okay? So, the next quantum number is the angular momentum quantum number. And I hope this blows your mind. Okay? There's a lot of stuff to write here. And blah, blah, blah. It's the orbital set. This identifies the orbital set. So this identifies whether that last electron is in an S, a P, a D, or an F orbital. So that picture that we just looked at with all the orbitals on it, the L value, the angular momentum quantum number, identifies which set the electron is in. And it's got several different values. Each orbital can contain 2 electrons. We already talked about that. Here. I want you to look at this periodic table over here. And if you need to move so you can see better, feel free to move. So, let me get a different color. I need a different color. These first 2 columns, that's L equals 0. These first 2 columns, every electron that goes, the last electron that goes in for any of those elements is in an S orbital. L equals 0 means that it's an S orbital. Owen?
That include hydrogen?
It does include hydrogen. And it includes helium. Thank you for asking that. And it includes helium. But you don't really see that because helium's on the other side, right? But it includes hydrogen and helium as part of that. We refer to it as the block, the S block. So now, I want you to look back at the picture of all the orbitals. How many S orbitals are there? In your resource packet, look back at the first picture we looked at. How many S orbitals are there? There's 1. And each orbital can hold how many electrons? 2. How many columns are in that S block? Not blowing your mind yet?
They all just feel like random coincidences that don't follow the same law.
Yeah, I think sometimes the organization of the periodic table did result in those coincidences, but the organization of it, this kind of all fell out of it. All right, so here's the P block. The last 6 columns, that's the P block. That does not include helium. Okay, it does not include helium. Helium is part of the S block. These last 6 columns, that's where the L value is 1, and that's the P block. So how many P orbitals are there in that set?
1.
P. There are 3 of them, right? 3 P orbitals. And each orbital can hold 2 electrons for a total of how many electrons? 6. Now how many columns are in the P block? 6. Still not blowing your mind?
But like, what is the connection? Like,
I like where you're going with that.
I feel like it's just random. I just feel like someone just started it too.
I like where you're going with that. Unfortunately, I can't show you that connection yet, right? We still have a few things we have to talk about. So then these transition metals, when those of you that are seniors, do you remember when we talked about the transition metals your freshman year and I told you they're funky, they do not behave themselves? Yeah, they're still funky, they don't behave themselves, but those transition metals are part of the D block. D block. And that is where L equals 2. So how many d orbitals are there in the set? 5. And how many columns are there in the transition metals? 10. Because each atomic orbital can hold 2 electrons. There are 5 atomic orbitals for a total of 10. 10 columns in the d block. Do you see where we're going with this? Not yet? Okay, that's okay. So these last 2 columns, or these last 2 rows down here at the bottom that are removed from the periodic table, these are the F block. This is where L equals 3. And I'm just going to go ahead and tell you, since you're all frantically trying to write things down, there are 7 orbitals in the F set. And there are 14 elements in that row in the F block. Because each atomic orbital can hold 2 electrons, there are 7 atomic orbitals. There are 14 elements across. Not impressed, huh? Not impressed? You guys are really making me earn my money. I'm just saying. Yes, Owen.
So how many orbitals are in P? Sorry, I don't know.
3.
3? Okay.
Do you know how to tell?
It says 1, 3, 5, 7.
Yes. So if you look at this picture, you just count them across. Not impressed? Really? Nothing?
I don't even understand it.
Oh, okay. I get that. You don't understand it yet.
At the moment.
Do you trust me?
I mean, I can't be impressed by what I don't know, but
You
Sure.
didn't answer the question. I'm starting to be a little
I'm worried.
nervous.
I'm nervous.
Do you trust me?
I think so. We'll see.
Wow. I think that might be worse.
I don't know, it just
Do I
feels
hear
like
I don't have a choice? Is that the next thing?
Yeah.
I mean, like, I'm just on for the ride. It is
Wow.
switching
I
slides.
feel loved and appreciated. It's fine. It's fine. It's not Tuesday. I'm gonna.
I mean,
hold it
they'll
in.
probably come together.
You gotta trust me. I know it's confusing, but we have to have a little bit of basic understanding before we can put it all, we're gonna tie it all together in a nice big bow. It'll be good.
I just thought everything made sense for about 0.5 seconds. And then we're like, the Boris model isn't true. And I'm like, oh, okay.
You knew it wasn't true because it made sense.
Exactly.
Right?
Why
So
I
there
don't
you
know
go.
if I trust science. What you're teaching.
Oh no, science is real. It's good. It's gonna be fine. All right. So I'm gonna go on. Okay, we already talked about that. All right. The next quantum number is the magnetic quantum number, M sub L. Bell rings in at 5 after? Okay. So M sub L, it is the specific orbital within the set. Okay? So here's what we've done. We've identified the energy level first, right? The principal quantum number. So instead of talking about 118 elements, we've narrowed it down to 1 row on the periodic table. After we identified that, we identified the orbital set. So now instead of all the elements in a row, we've narrowed it down to just a chunk of the row. With this quantum number, we narrow it down from a chunk to 2 elements. Okay? So this is the specific orbital within the set, and it is usually identifies the orientation of the orbital in space. The values can range, that's an L, from negative L, going by integers, negative L plus 1, negative L plus 2, all the way through 0, and then all the way up to 1, or all the way up to L again. Don't worry about that. I'm going to show you what that means. And we're going to label it on the periodic table, but we're going to do that tomorrow. I want you to do the writing intensive stuff today because I feel like that's where we're focused right now. And it doesn't make any sense. So just write it all down and we'll get to it. Okay? So the magnetic quantum number takes the entire orbital set and it identifies it down to a single orbital within that set. So if the element of interest is in the P block. There are 6 elements in the P block, but only 2 of them, there are 6 elements in the P block, but that's the whole orbital set. This quantum number identifies specifically which orbital that last electron is in. That narrows it down to 2 elements. I know that doesn't make any sense. It will, trust me. Yes, Chase.
How?
How what? How to trust me?
No.
You just got a leap. Just a leap of faith.
How does it narrow it down?
We have to identify the numbers. I'm going to take you through some examples, and when we explain it with the examples, it'll make sense.
So just don't ask me questions.
Right now, it's a leap of faith. It truly is. So if you don't trust me, then it's just writing information down. One more. There are 4 quantum numbers, right? The spin quantum number. Okay? This is the last quantum number. This identifies that electron. This is the key to knowing which electron is where it is. Okay? The options are spin up or spin down, and the values that this can have, they're positive 1/2 or negative 1/2. All of the other quantum numbers will have integer values. This is the only one that's a fraction. Positive 1/2 or negative 1/2. And that positive 1/2 corresponds to spin up. The negative 1/2 corresponds to spin down. Any questions about that? It's too bad Chase says you're not allowed to ask.
Wait a minute.
I feel like it's not gonna make sense until we learn. So I'm just not gonna be worried until we finish what I'm doing, and then I don't know it.
Yes. Are you trying to suggest that you trust me?
I'm saying I have no choice.
I feel like he's afraid to say you trust me. Don't worry, the squirrels stay contained, it's fine.
I'm just unsure.
Yeah, it is.
It's like, there's all these exceptions, it's like life, it's complicated and fuzzy, like the little orbital, okay? So I feel like that's how chemistry is, so I feel like you're never gonna be able to give us like a sufficient answer, and that's gonna annoy me.
Did I give you a sufficient answer last year?
I like numbers though, and like, there was like always a specific number, and that's just not the case.
At the second half of the year,
Actually,
you're gonna hit your stride. So, I know, there are all kinds of exceptions, because in this world, this quantum world, what we observe on what I'm gonna refer to as a macroscopic level, what we can observe, is clunky. It's physics. But when we get down into that quantum realm, everything changes. And even the things we've sort of taken for granted, it becomes very specific, and the details, chemistry will get you in the details. That's the hardest part of chemistry. There's an exception to every rule, except that one. Dang it. But, I promise you, the majority of the stuff that we talk about, and the majority of the exceptions that we see, are gonna come back to this stuff. So, let's see where we're going.